All right, let's go ahead and get started. Thank you all for coming. As usual, during these reviews, anytime you have questions on either the exact problem I'm working on or anything that you think is relevant to that topic, please go ahead and stop me, and I'll be happy to just slow down and pause for questions. But with that, let's just get right into it. So the first question here, we're calculating the work when a sample of N2O expands from 3.75 to 8.25 liters against a constant pressure of 957 torr. So there's only one equation we have to worry about for work. We're always talking about expansion work or contraction against a constant pressure or with a constant pressure. So it's just the negative of that external pressure times the change in volume. So you just need these two terms to be able to calculate work. We have to be a little bit careful with units in these problems as always. So we look at the answer choices here. They're all given in liter atmospheres, which is not the most conventional unit for work or energy, but certainly could be used, and that's what we're using here. So the unit tells us we need to have, in this case, we need to have our delta V needs to be in liters, and then our pressure needs to be in atmospheres. So those are the two conversions we have to keep in mind when we're doing this. So our pressure is given to us here in torr, so a conversion that we have to use a lot in this part of the course is that if we want our external pressure to be in atmospheres and we're starting in torr, we have to divide by 760. So it's 1 atmosphere per 760 torr. So that comes out to 1.26 atmospheres. So that's the pressure in the correct units. Make sure we keep the minus sign out in front. And then delta V is just our change in volume, which is the difference of final volume minus initial. So we're going from 3.75 to 8.25. So 8.25 liters is our final volume, and our initial volume is 3.75. So we just subtract those two for delta V, and that comes out to minus 5.67 liter atmospheres. All right, so the sign is important. We have the negative sign out in front of the equation, which tells us that anytime the gas is expanding, which means delta V is positive, it's going to be a negative work, meaning that the system is delivering work or doing work. So that's what we see here, and that comes again straight out of the equation as long as you remember to leave the minus sign in there. So the correct answer then would be choice B for this one. The other thing, as I said, we could ask you to do sometimes is convert this into the more conventional unit for work and energy, which is joules, and so we have to remember then that 1 liter atmosphere, which is the units we have here, is equal to 101.3 joules. So that's another conversion that you may have to do in some of these once you get your answer from P delta V, converting it into a different unit if that's what the answer choices are, if that's what the question specifies. All right, questions on this one or on this topic? All right, if not, let's go on then. Things are out of order here. I didn't leave a question out. I just reordered them and then didn't renumber them. So anyway, this is number 3, but it's actually the second question. And then number 2 will be the third question to keep things confusing for a while. So what is the change in internal energy when a system absorbs 965 joules of heat and has 456 calories of work done on it? So we've learned, a few different contexts for delta E and delta H and things that are related. But in this case, when we're talking about change in internal energy, we're specifically talking about delta E. And you want to think about this as being the combination of Q plus W, where heat is the work, Q is the heat, which is either released or absorbed by the system. W is the work, which is either done by the system or done to the system. W we know how to calculate, as we saw in the last one, if we need to. In this case, though, we're just giving you the values directly. So delta E is Q plus W. Now what we're looking for here is the internal energy in kilojoules. And we notice that the two terms that we have, this is our Q here, 965 is in joules, and then the work is 456, but it's in calories. So one other conversion factor which I gave you here is that 1 calorie is 4.184 joules. So anytime we're adding two numbers together, they have to be in the same units before we can add them. So we need to make sure that the two numbers are in the same units before we add them. So let's talk about the heat and the work separately then. The other thing too is that in these types of problems, we're not going to necessarily give you the sign for Q and W directly. We're going to give you the sign for that, whether it's positive or negative, is going to be determined by whether the work is being done on or by the system and whether the heat is being absorbed or released. So you have to read the problems closely to see what the correct positive or negative sign is. So for Heat, it says that we're absorbing heat. Q is absorbed. And whenever heat is absorbed by the system, that means it's positive. Okay, so the heat is going to be given as positive 965 joules. If it was heat being released, it would be negative 965. But here it's absorbed. And then if we talk about work, work is done on the system. So if work is done on, that means it's also positive. If work is done by the system, that would make it negative. So we have to keep the sign straight. So our work done on is 456 calories, also positive, but we have to get that into the same units as the previous one to be able to add them together. So we're going to multiply that by 4.184 joules per calorie, and that comes out to 1908. All right, and so then when we put both of those terms into our delta E equation, heat plus work, Q plus W, we get 965 joules plus 1908 joules is 2873, and then all the answer choices here are in kilojoules, so we have to divide by 1,000 to get 2.87 kilojoules. And that would be choice A then. Alright, so the two important things here are making sure that the signs of Q and W are correct, when that's going to come from the description of each of those processes that you get in the problem itself. And then once you know the signs, you just add them together, but they also, of course, have to be in the same unit before you do that. All right, so questions on this topic? All right, let's keep going then, because I'm sure there will be times later on we'll have to stop. All right, question number 2, which is the third in the set. The numbers should be correct after this. All right, so here we're talking about sort of some conceptual points about delta H. So here we're told that the reaction between HCl and NaOH is exothermic. Which of the following statements about this process is correct? So we had a bonus quiz that was a lot like this, as it turns out. So if we're going to think back to that and think about the different concepts we know about delta H. So the first one deals with the sign of delta H. So we're looking for the correct statement here, the one that is true. And if the reaction is exothermic, what we have to remember is that means that delta H is less than 0. So we're talking about an exothermic process here, as we're told. And exothermic means a few different things, but the most important one is the sign of delta H. It tells us that delta H is negative or less than 0. So that statement is incorrect. That should be a negative delta H if you're talking about an exothermic reaction. If we go through the next answer choice B, the enthalpy of the products are greater than the enthalpy of the reactants. So we have to think about this in terms of what delta H is referring to in a chemical reaction. So delta H, again, anything with delta in front of it means final minus initial. So it's delta H would be the final enthalpy minus the initial enthalpy. In the context of a chemical reaction, the final is the products, the initial is the reactants. So we can think of delta H as enthalpy of the products. Now, we don't usually measure or report absolute enthalpy values, but we can think about it this way. For delta H, is products minus reactants. And as we said, this is going to be less than 0 for an exothermic reaction, which we're talking about here. So if we think about what that means, then it means that in order for this to be true, the enthalpy of the products have to be less than those of the reactants. If we subtract two numbers and the result is negative, that means the first number is smaller than the second. So the enthalpy of our products must be smaller than the enthalpy of the reactants, which is the opposite of what choice B says. So this one is also incorrect. In an exothermic reaction, the enthalpy of the products are smaller because the delta H is negative, less than 0. All right, and then choice C deals with what happens in the surroundings. So in an exothermic reaction, choice C says the temperature of the surroundings increases. So remember that when you have an exothermic process, meaning delta H is negative, which also means that the heat measured at constant pressure is negative. Delta H is that heat value at constant pressure. The fact that it's negative tells you that heat is released from the system. And if heat is released from the system, it goes into the surroundings, and that means the temperature of the surroundings will increase. So anytime you add heat to the surroundings, that temperature increases. That's how hot packs work. And if you do any sort of exothermic reaction, you're going to feel the surroundings getting warmer. So that one actually would be correct, that the temperature of the temperature of the surroundings increases for any exothermic process. And then finally, choices D and E, we've sort of identified choice C as the right answer, so we don't have to necessarily go further, but let's talk about these two just to make sure. D tells us about is that talking about the bonds in the products are weaker than the bonds in the reactants. And so this goes way back to some things we learned back in chapter 3. We're talking about relative bond strengths of reactants and products. So if we think about delta H, it's, as I said, similar to delta E. And as we learned back in chapter 3, we can estimate this by taking the sum of the bond energies for all of the reactants and subtracting the sum of the bond energies for all the products. So this equation is sort of in the opposite order. It's reactants minus products. That's because of how bond energy is defined, as we talked about back then. But again, this number has to be less than 0 because we're talking about an exothermic process with a negative delta H. And so if this is less than 0, it means that, again, the first number of reactants must be smaller than the second. So in this case, when you have an exothermic reaction, the products are greater than reactants in terms of their bond energies. All right, so that means this one in the answer choice says that the bonds in the products are weaker. That would be false also. When you have an exothermic reaction, the bonds in the products are stronger. And you release that extra energy from the bonds into the surroundings. All right, so that's thinking about, again, an alternative definition of delta H in terms of bond strength, which we touched on back in chapter 3, although we called it delta E back then because we didn't have those two distinguished, but they really, in most contexts, mean the same thing. And then finally, choice E, we kind of already touched on this one. It says the reaction absorbs heat from the surroundings, but in any exothermic process, it's actually going to be releasing heat to the surroundings. So in an exothermic process, heat is released. So that one's also going to be false. So clearly then choice C is the only one that is correct out of all of these. And that deals with, again, the temperature of the surroundings increasing during any exothermic process. All right, so any questions on this concept or this question in particular? Yeah?
Can you explain D again?
All right, so D, if you... do you guys remember back in chapter 3 we talked about, we called it delta E back then because we hadn't introduced delta H, but we said that the energy change for a reaction is given by, or estimated by at least, the sum of the bond energies of the reactants minus the sum of the bond energies for the products. We had that sort of approach back then for estimating delta E, which really is delta H. And so we're using in this case then that alternative definition and saying that the sum of the bond energy of the reactants minus the sum of the bond energies of the products is delta H. And that number has to be less than 0 for any exothermic process, which is what we're talking about here. So if this difference is less than 0, that means the first number is smaller than the second, which means that the reactants have smaller bond energies than the products. All right, which is the opposite of what this answer choice says. And so in an exothermic process, that would be the case. In an endothermic process, the bonds in the reactants are stronger than the bonds in the products. It's opposite. Okay? All right, anything else? All right, moving on to now some sequentially numbered questions for the rest of today. So let's say at number 4, we're talking about a thermochemical equation. And I like this question because it actually combines concepts from both Chapter 7 and Chapter 8. The test is on both of them, so we could ask you to combine things from both of those. So here we have a gas phase thermochemical equation. It's a combustion reaction of ethane. And we want to know what is the enthalpy change when 12.5 liters of ethane measured at 25 Celsius and 780 torr is burned in air. And so in these types of problems with thermochemical equations, typically what you're doing is we're giving you a balanced chemical equation and we're giving you the delta H for that process, and we want to know how much heat or how much enthalpy change is involved when we're doing the reaction on some given scale. So this equation here, this thermochemical equation, tells us that when 2 moles of ethane reacts with 7 moles of O2, we get 4 moles of CO2 and 6 moles of water. And the enthalpy change for that process is minus 2855 kilojoules. That's how much heat would be released if we conducted the reaction with that many moles of each reactant forming that many moles of product. However, here what we're looking for is what is the enthalpy change if we're instead using 12.5 liters of ethane, which is measured at that temperature and pressure, which may or may not be exactly equal to the 2 moles we have here, so we have to figure that out. So in these types of problems, we almost treat them like stoichiometry. We know what the enthalpy change is for the reaction in terms of moles of reactants and products. Let's figure out how many moles of reactants or product we actually have, and then use that and then we use a conversion factor to determine enthalpy change for that. So the first thing we need to do, just like any stoichiometry problem, is figure out how many moles do we have. So what we're told here is that we have 12.5 liters of ethane, 25 Celsius, 780 torr. We should immediately think of the ideal gas equations, PV equals nRT. Because if we know the pressure, volume, and temperature of the gas, which we do, we can use PV equals nRT to find out how many moles of that gas we have. And then we can relate that to whatever stoichiometry, or in this case, thermochemical calculation we're doing. So PV equals nRT, we have to get the pressure in atmospheres to be able to use this equation, because we have our standard value of R is in liter atmospheres per kmol. So our pressure in atmospheres, again, that same conversion that we do many times, 780 torr is the pressure, and we divide by 760 to get it into atmospheres. So that comes out to 1.03 atmospheres, so just about 1 atmosphere. And then that means the moles of ethane, we can just rearrange the ideal gas equation and say that it's equal to PV over RT. And so the pressure is 1.03 atmospheres. We're told that we have 12.5 liters. So that's the volume, we don't have to convert that. And then RT, R is going to be the universal gas constant, which is on your periodic table, but it's this value here, 0.0821. Whenever using the ideal gas equation. And then the temperature is 25 Celsius. We need to convert that into Kelvin anytime we're doing any calculations with gases using absolute temperature. So this, we're going to add 273 to that, and that's actually 298 Kelvin in the correct unit. So we'll put that in as 298. And so what we find out is that this amount of C2H6 at this pressure, volume, and temperature corresponds to 0.56 moles. And then if we know we have 0.562 moles of C2H6, we can use the thermochemical equation that we're given to figure out what would be the delta H when that many moles of C2H6 is consumed in the combustion reaction. So then our enthalpy change delta H is going to be, we have 0.526 moles of ethane, C2H6. And then from the thermochemical equation, we see that the enthalpy change is minus 2855 kilojoules. And that's the enthalpy change when 2 moles of ethane burn, because there's a coefficient of 2. Yes? So that's using PV equals nRT. Is it 526 or 562? My inability to talk and write has reared its ugly head. Okay, so 526 is the correct number that we get from PV equals nRT. So then we translate that down to this calculation down here. 526 moles times the enthalpy change, which is per 2 moles of C2H6. Again, that 2 comes from the fact that the coefficient in the balanced equation, the balanced thermochemical equation, is a 2 there. Sorry, I'm jumping around here. And so when we multiply that out, we get minus 750.9 kilojoules. If this was Blackboard, you would just enter in the number. All right? And, please in Blackboard, I remind people of this many times, follow the instructions for how many decimal places you should have, or what format your answer should be in. So I'm not opposed to going back and regrading if you miss it for a stupid reason, but there's a lot of you, so I'd rather not have to do that too much, and in some cases it can cause your answer to be too far off if you do too much rounding. So save your rounding for the end is the point, and follow the directions for how many decimal places you should include in your answer. The point of that is not that the answer will be automatically marked wrong if you have the wrong number of decimal points, but it just makes sure that you don't round it too much to be off from what the acceptable answers are in Blackboard, okay? So that's how we would enter it in Blackboard, and that's how we do the problem. So any questions on this one, or the concept of thermochemical equations? All right, on to the next one then. All right, so in this problem, we're taking 5 grams of copper, 5-gram copper slug, with a given specific heat capacity of 0.385 joules per gram degree Celsius. We're heating it to 100 degrees Celsius, and then we're placing it into 10 milliliters of water, which is initially at 23 Celsius. So we want to know what is the final temperature of the water in Celsius, assuming that no heat is lost to the surroundings. So again, enter your answer with 2 decimal places. We'll follow those directions at the end. So in this type of problem, we're talking about heat transfer between an object and a calorimeter, which can be thought of as heat transfer between the system and the surroundings. And so whenever you have this situation, there's going to be some heat that's lost or gained by whatever you're putting into the calorimeter, in this case a piece of copper, and that's going to be equal in magnitude but opposite in sign to whatever heat is lost or gained by the water that you're putting it into. So they're at two different temperatures. They're going to transfer heat between them. The amount of heat that's transferred is some number, Q, and it's going to be equal and opposite in signs depending on whether you're talking about the system or the surroundings as your reference point. And so then what we can do is, using this, we can rewrite this in terms of really the only equation for Q that we know, which is mc delta T. So that means that the mass of copper times its heat capacity times its change in temperature is equal to the negative of that for water. You can put the minus sign on either side of the equation. It doesn't matter where the minus sign goes, but it has to be on one side of the equation because they're going to be equal in magnitude but opposite in sign. So if you're going to set them equal to each other, they have to have a negative sign out front of one of those sides of the equation. So that's the equation we're going to solve. And initially you look at this and you might think, well, we have two unknowns. We have delta T for copper, delta T for water. And that's technically true, but we're going to rewrite those, remembering that for both of these, delta T is equal to the final temperature minus the initial temperature. And the final temperature, TF, is going to be the same for both of them. So the heat transfer stops when the two objects that are in contact with each other, in this case the copper and the water, when those get to the same temperature, that's when there's no more heat transfer. So that TF value is the same number for both of them. So we can then rewrite the equations as in putting the numbers in. So the mass of copper is 5 grams. The heat capacity for copper is 0.385 joules per gram degree Celsius. Because we're talking about a difference in temperatures, we can use Celsius or Kelvin for this. So for copper, the delta T can be written as the final temperature, which is our unknown, minus the initial temperature, which for copper is 100 degrees Celsius. And that's equal to, with a minus sign out front, the mass of water, which was, we have 10 milliliters of water, so that's equivalent to 10 grams. Remember, the density of water is 1. The heat capacity for water, which I don't think I gave you here, but is the one heat capacity you should be familiar with, is 4.184. And a lot of problems will give that to you. And then the delta T for that is going to be final temperature, again, same number, minus 23 degrees Celsius, which was the initial temperature for water. All right, so the water started at 23, so its delta T is going to be TF minus 23. Copper started at 100 degrees Celsius, so its delta T will be TF minus 100. So now we have one equation with only a single unknown, which is final temperature, T sub F. And so I'm not going to work through the algebra. The algebra is not too terrible here, but you have to do some distribution and rearranging and things, so it's not trivial either. And we get final temperature should be 26.39 degrees Celsius, specifying 2 decimal places, as we said in this problem. All right, and so if you're doing problems like this that ask you to find the final temperature when you're mixing two things together, one that's hot, one that's cooler than that, your number should be in between the two values. So the water started out at 23, the copper started out at 100, and so whatever number you get should be between 23 and 100. If it's not, then you mess something up. And then you use, again, the equations that we gave here to figure out what that exact number would be. All right, questions on this one? Okay. All right, so the next question also deals with calorimetry, but here we're doing a reaction inside of a calorimeter. So the other application we have for calorimetry is measuring enthalpy changes for reaction, and that's what we're doing here. So we have a bomb calorimeter, which has a heat capacity of 9.25 kilojoules per Kelvin, and we're going to fill it with 1 liter of water. If we take 5 grams of acetic acid and burn it in the calorimeter, that raises the temperature by 5.4 degrees Celsius. We want to use this information to determine the enthalpy change in kilojoules per mole for the combustion of acetic acid. So what we're doing here is we're burning 5 grams of acetic acid, and we're figuring out how much heat is released by that process. Then what we really want to do is then determine how much heat is released when a full 1 mole of acetic acid burns in kilojoules, so we're doing kilojoules per mole. Alright, so what we have to do first in any sort of calorimetry problem where we're doing a chemical reaction inside the calorimeter is we're going to calculate the heat that's absorbed by the calorimeter. So this is an exothermic process, we're burning something inside of it. So the calorimeter is going to absorb whatever heat is produced by that burning process, that combustion reaction. So the heat for the calorimeter is given by two terms here, and depending on the information in the problem, we're going to either use one of these two terms or both of them. So if the calorimeter has water in it, some amount of the heat is going to be absorbed by the water, and that amount of heat is given by, again, mc delta T. So if we know how much water is in our calorimeter, we know the heat capacity of water and delta T. That portion of the heat is absorbed by the water, and then the calorimeter itself, which is whatever is holding the water and the other parts of the calorimeter, that's going to absorb some of the heat as well. And we give that by just an overall heat capacity, which I'll abbreviate with capital C, times delta T. All right, so this amount of heat, this first term is the amount of heat that's absorbed by water. The second term is the amount of heat that's absorbed by the calorimeter itself. And in this problem, we have information about both of those. So we're told that we have 1 liter of water in the calorimeter, so we know how much water is present. We're also told that the calorimeter has a heat capacity of 9.25 kilojoules per Kelvin, so we know both of these pieces of information, so we're going to have to use both of these when we calculate the heat term for the calorimeter. So putting some numbers in then, we have to also be a little bit careful with units here because we see that the heat capacity for water is in joules per gram Kelvin. The heat capacity for the calorimeter is in kilojoules. So we need to convert one of those two terms to be able to add them together, as we have to do to find the heat for the calorimeter. So what I'm going to do is I'm going to convert the first term because our final answer, we want that to be in kilojoules. So let's get everything into kilojoules as quickly as possible. But you could have also started in joules and converted to kilojoules at the end. There's no wrong way to do that. So anyway, what we have for the water is the mass of water has to be in grams. So we have 1,000 grams of water because it's 1 liter of water, which is 1,000 milliliters, which is 1,000 grams. The heat capacity for water is 4.184. And then the delta T was 5.4 degrees Celsius, or 5.4 Kelvin. Remember, in terms of delta T, those two are interchangeable. So that's the amount of heat absorbed by the water. And then for the calorimeter, the heat capacity is 9.25 kilojoules. So this term would be in joules. So let's multiply it by 1 kilojoule over 1,000 joules to get that in kilojoules, so that we can add it then to the term for the calorimeter, which is 9.25 kilojoules per degree Celsius is the heat capacity times the same change in temperature, 5.4 Celsius. So both the water that's in the calorimeter and the calorimeter itself change by the same temperature. They're all in thermal equilibrium with each other. And so when we work this out, what we get is that the amount of heat absorbed by the calorimeter was 72.5 kilojoules. Or alternatively, we could have left the first term in joules, converted the second term from kilojoules to joules, and multiplying by 1,000, we would have gotten 72,500 joules. But as long as you keep the unit straight, it doesn't matter which one you use or when you convert them. So that's the amount of heat that's absorbed by the calorimeter. And remember, all of that heat that was absorbed by the calorimeter came from the chemical reaction that was happening inside of it. And so then the next step is going to be saying that if we want to know the heat for the reaction, that's equal to the negative of the heat for the calorimeter. So we just plop a minus sign in front of it, and that's the amount of heat. That's the heat change, the enthalpy change for the reaction itself, which is minus 72.5 kilojoules. But again, that's the amount of heat that was released, or the enthalpy change when we burned 5 grams of acetic acid. What we're interested in for our final answer is the amount of heat that was released when we burned 1 mole of acetic acid. We're looking for the answer in kilojoules per mole of acetic acid. So to do that, what we have to do is say that the delta H in kilojoules per mole is going to be the heat for the reaction divided by the moles of substance that we burned. So that ratio, kilojoules per mole, will come out of this. And so what we have then is the heat of the reaction we just found is minus 72.5. And we have to divide that by moles of acetic acid. So the moles of acetic acid we're not given directly, but we know we have 5 grams. So the moles that we're burning of acetic acid, I'll do that up here so I don't run a room down there. We have 5 grams. And then we just use the molar mass, which was nice enough to give you here. So that's 60. That's that number there, 60.02 grams per mole. So that comes out to 0.0833 moles. So that's how many moles of acetic acid were burned in this process. So if we take the amount of heat that was released and divide it by that, try to keep that as much as I can so you can still see it. We divide the heat of the reaction by the number of moles of substance, that gives us kilojoules per mole. and it comes out to minus 870.3 kilojoules, or kilojoules per mole, I guess is the better way to say it. And that's the number we would put in, minus 870.3. All right, so these calorimetry problems, when you're dealing with chemical reactions and trying to find enthalpy changes, it's really the same series of steps. You're going to find the heat for the calorimeter using some combination of MC delta T or just heat capacity times delta T. In this case, we use both. The negative of that is the heat for the reaction, and then if you want the heat of the reaction per mole of substance, which is usually how we report it, you would take the heat of the reaction and divide it by moles of substance to do that. So it's a series of steps. The other thing to be careful of that a lot of students do on these is we're telling you here that we're burning 5 grams of acetic acid, and it's very tempting to put that 5 grams into MT delta T. But remember that when we're calculating heat for the calorimeter, the mass that we put in is the mass of the water that's in the calorimeter, not the mass of substance that we react, or in this case burn, during that process. All right, so be a little bit careful with what numbers we use where, because these problems have a lot of numbers associated with them and a few different steps involved. But we only want to use the mass of water in the calorimeter when we're calculating the heat that's absorbed by the calorimeter. All right, so any questions on this one or calorimetry in general? Oh, sorry, yeah.
How did you get delta H?
Well, what we're looking for is we're specifying the enthalpy change in kilojoules per mole. So very commonly, we especially for combustion enthalpies, we report that per mole of substance. So if you know how much heat is released in the reaction that corresponds to 5 grams, if you divide the two, the amount of heat by the moles, that will give you kilojoules per mole. So you're normalizing it per mole of substance. Because when you do a reaction in a calorimeter, the amount of heat that you measure is determined by how much substance you use. But typically when you report that value, you would want it either per mole or sometimes per gram of substance to normalize it to a certain amount. And so we have to divide those two quantities to get that in the right form. All right, any other questions? All right, moving on, number 7. All right, here we're calculating the delta H of formation for B2H6 diborane using the following data. So we give you 3 chemical equations, we give you their delta H values, and we're asking you to find another delta H, in this case a delta H of formation. So this is what we would refer to as a Hess's law problem. We're taking known chemical equations with known delta H's, we're combining them in different ways to find delta H for another process. Now in this case, we're not directly giving you the chemical equation that you're trying to find delta H for, but we're telling you that it's a delta H of formation. That little F there tells us it's a formation enthalpy. And remember that formation enthalpies refer to specific chemical reactions, and those chemical reactions are forming 1 mole of the compound from the elements. So the equation that we're trying to find delta H for is the formation of B2H6. So B2H6 would be the product, and I guess it's a gas if we want to keep our states of matter straight. And the formation equation refers to forming that compound from the elements in their standard state. So the 2 elements are boron and hydrogen. The standard state for boron is just B, which is the solid, and then we're going to combine that with hydrogen, in this case 3 H2s, to keep it balanced. And so this is the chemical equation that corresponds to the formation of B2H6, and that's what we're trying to find delta H for. So what we have to do then is we have to figure out how do we combine these 3 equations such that we can add them together in a certain way to get this equation here. So what I like to do is number the equations, 1, 2, and 3. And then what you want to identify is you want to look at the reactants and the products in the equation that you're trying to find delta H for, which is this one here. So those are the reactants, and there's the one product. And figure out which of these equations they appear in up here, and ideally find ones where they only appear once in one of those equations. So if we look at our first reactant, we have 2 borons as a reactant in this equation. And where does boron appear in these equations up here? The first one, right? So we're going to use the first equation, but the first equation has a coefficient of 4 in front of boron. We want to have a coefficient of 2 in the equation we're interested in, so we're going to have to take this first equation and we're going to have to multiply it by 1/2. So if we take the first equation and multiply it by 1/2, we take all of these coefficients and we have them, so we get 2b's, I'll leave out the states of matter because they're not important for this problem, plus 3/2 O2 going to B2O3. And then the delta H for this, when we modify it, is going to be 1/2 times that first delta H. So if we multiply all the coefficients by 1/2, we also multiply the delta H by 1/2. So that's going to be 1/2 times this number here, which comes out to minus 1254.6. So that's half of that delta H when we modify it. So that gives us 2 borons on the reactant side. So we've taken care of that reactant in the overall equation. We look at our next one, which is 3 H2s. And we see that H2 only appears where? In the second equation. The coefficient for H2 in the second equation is 2. We want it to be 3, so we're going to have to take the second equation and multiply it by 1.5, or 3 over 2. Alright, so we're going to modify the coefficients in the second equation such that the coefficient for hydrogen becomes a 3, which is what we want. So we get 3H2. We have to multiply the coefficient for O2 also by 3/2. And then the product, 3/2 times 2 would be 3. So that's going to form 3 waters. And since we multiply the coefficients by 3/2, the delta H gets multiplied by the same number. So delta H for this modified equation is going to be 3/2 times the second delta H. So it's going to be this number up here, minus 571.7, times 3 over 2, which comes out to minus 857.6. So our hydrogen we're taking care of. And then finally we see that our product is B2H6. B2H6 only appears in the third equation, but it appears as a reactant in the third equation. We want to put this on the product side, so we have to invert or flip this third equation here to put B2H6 over on the product side. So we're going to take the inverse of the negative of equation 3, which means the reactants become the products and the products become reactants. So B2O3 plus 3 H2Os going to B2H6 and 3 O2s. So that takes care of B2H6. The delta H for this, because we flip the reaction, we just take the negative of the original delta H. So that becomes, instead of negative 2147, that becomes positive 2147.5. So if we invert the reaction or flip reaction products, we just change the signs of delta H. So then we should verify that when we add these three things together, we get the overall equation we're interested in. So we took care of the reactants and products, so if we did our job right, it should work out. But let's also make sure that anything that's not supposed to appear in this equation cancels out like it should. So on the reactant side, everything on the left side of the arrow carries over. We get 2 borons. Here we have 3/2 O2 that would carry through. We have another 3/2 O2 on the left of the arrow. So we have 3 O2s on the left side of the arrow, but they're going to cancel out with the 3 O2s that are on the right side of the arrow down here when we add them all together. So the O2s cancel out. From the second equation, we have our 3 H2s that carries through, which is what we want. And then from this third equation, we have B2O3 on the reactant side, but it cancels out with the B2O3 that's on the product side up here. So these two are on opposite sides of the arrow, so they cancel. And then same with the 3 H2Os. We have a 3 H2O on the reactant side here, but that's going to cancel out with the 3 H2Os that are on the product side there. So the only thing that's left on the product side, once we cancel everything out, is just the B2H6 that we want. And then the delta H is just going to be the sum of these three numbers after we've modified them and added the equations together appropriately. So we get minus 1254.6 minus 857.6 plus 2147.5. Sorry, I'm writing small here. And then that comes out to 35.3 kilojoules if I did the math right. Or currently read as kilojoules per mole. But anyway, that corresponds then to the correct answer being choice B, 35.3. All right, so we have to add the three equations together. We have to modify the delta H's and then add those together at the end. So questions on this one? Does that make sense, everybody? Is that a question or stretching? Sorry. Okay. Sure. Potentially, yeah. So there's the 3 gas laws. We'll get to some of them maybe a little bit later in this, but the 3 gas laws that you should know are Boyle's law, which is pressure and volume, Charles's law, which is volume and temperature, and then Avogadro's law, which is volume and number of moles. So those were the 3 that we introduced on the way to deriving the ideal gas equation. You should know which one is which, although for the numerical problems, as long as you know the ideal gas equation, you can always use that as your starting point. You got a question in the back? No, so we cancel, there's 2 3/2 on the reactant side that add together to be 3. And then on the product side, we have a 3O2 down here. So it's those 2 canceling with that 1. So the sum on each side is 3, and they cancel out because of that. Yep. Because we're talking about a formation equation, and for a formation equation, the compound is always on the product side. So because we're looking for delta H of formation for B2H6, so what that means is the chemical equation has to have 1 mole of B2H6 as a product, and then the elements that make up B2H6 would be the reactants in that. So that's coming down to the definition of what a formation equation is. Anything else? All right, onward and upward. All right, and this one here, we're also trying to find an unknown enthalpy of formation. So we have, we're looking for the enthalpy of formation for ammonia. We have delta H of formation given for NO2 and water, and we have this equation here with also its delta H given. Now, in reality, what we're doing in this problem is the same as what we did in the last one. We don't have to necessarily write out everything in as much detail, because we know if everything that we're talking about is a delta H of formation, we're giving you delta H of formation for NO2 and H2O, we're asking for delta H of formation of NO3. In this case, what we can use is sort of that shortcut equation, which is that the delta H for the reaction is equal to the sum of the delta H's of formation for the products minus the sum of the delta H's of formation for reactants. And to be consistent with how I wrote it before, you would put little coefficients here, m and n, to remind you to multiply them by the respective coefficients that you have in the chemical equations, because each delta H formation is per 1 mole, so if you have coefficients, you have to multiply by that. So we learned this equation as a way of finding delta H if we know the delta H of formation. Here we're going to use this equation, but our unknown in this case is one of the delta H of formation values. So conventionally you would use this to find delta H, but here we're given delta H, but we don't know the delta H for one of our reactants, NH3. So then we can just start putting the numbers in that we have. So the delta H for the reaction that we have here is given to us as minus 1134.4. And that's equal to the sum of the delta H's of formation for the products. So the products, we have 4 NO2s. And the delta H of formation for NO2 is given as 33.2. The other product is 6 waters, and the delta H of formation for H2O gas is given as minus 241.8. So that's the sum of the delta H of formation for products, and then we subtract the sum of the delta H of formation for the reactants. Our first reactant is NH3, and we don't know what its delta H of formation is. That's what we're trying to find here. But there's 4 moles of it, coefficient of 4, so we have to make sure we multiply that by 4. And then the other delta H of formation we need is O2. We're not given that value, but what is the delta H of formation for O2 gas? 0, because it's an element. So 7 times 0, that just doesn't come in at all. So anytime you have a pure element as one of your reactants or products, the delta H of formation for that would be 0, so we don't even have to worry about it. So then in this equation, our only unknown is the delta H of formation of NH3, which we're trying to find. And so we just do a little bit of algebra and find that the delta H of formation for NH3 comes out to minus 45.9 kilojoules per mole. So enthalpies of formation are sometimes written in kilojoules, sometimes written in kilojoules per mole. I think kilojoules per mole is more appropriate, but at any rate, just pick the number that's right, minus 45.9 kilojoules or kilojoules per mole. Okay? So in this case, we use this relationship between delta H for reaction and delta H of formations, but we're solving for one of the delta H of formations. So we can only have one unknown here because it's just a simple equation, but in this case, the unknown is one of the formation values for a reactant. Questions on this one? All right. So again, we could have gone through all the process of writing out the equations like we did last time, but for delta H of formation, it's not necessary to do that if you have this equation in mind. All right, the next question here is kind of a fun one. give a second for my tablet to reorient itself. There we go. All right, so methanol is being considered as a possible fuel source for the future. So really what this problem is, as you'll see, is just a whole bunch of conversions. It sounds like it's a complicated problem of some sort, but really what it is just unit conversions. And so it's considered as a possible fuel source for the future. The combustion enthalpy of methanol is minus 715.0 kilojoules per mole, which means that when we burn 1 mole of methanol, we get 715 kilojoules. And then, of course, if we're using it as a fuel, we use that energy to do something. And it has a density of 0.792. If we burn 1 liter of methanol, so let's say we take a liter of methanol and burn it, and we produce electricity, how long would it power one 60-watt light bulb? So people don't use incandescent bulbs anymore, but 60 watts is a typical light bulb that you would find in like a table lamp or something. And we're assuming 100% efficiency here. So we're figuring out how long will this light bulb last if we burn this much methanol. And it's going to be, as you see, a roundabout way to do here, but what we're going to do is just sort of follow the units to tell us where we have to go. So we're looking for how much time we can burn a light bulb for. So we know the wattage of the bulb, which is how many joules per second it consumes. We know how many kilojoules are produced by methanol. So hopefully things are starting to piece together a little bit. But let's start with what we're given, which is that we're burning 1 liter of methanol. Now methanol is a liquid, so if we're going to convert liters into moles, we can't use ideal gas equation. We can't use can't use molarity. What we're going to use instead is the density to get it into grams, and then we'll use the molar mass to get it into moles. So the first thing we're going to do is find out how many moles of methanol we have, because that's going to allow us to figure out if we burn that much methanol, how much energy do we get. So when we convert this into moles first, we can say that there's 1,000 milliliters per 1 liter. And there may be more than one way to do this problem, so if you find out an alternative one that's numerically equivalent, that could work. But we're going to start by converting into milliliters the way that I did it. Once we know how many milliliters of methanol we have the density that allows us to go into grams of methanol. So there's 0.792 grams per milliliter. That's what density tells us. And then once we have grams of methanol, as I said, we can convert it into moles by using molar mass. So the molar mass is 32. So 1 mole of C4H4O has a mass of 32.0 grams. All right, so that's how many moles of our fuel we have. And if we know how many moles of our fuel we have, we can use its combustion enthalpy, which is kilojoules per mole, to figure out how many kilojoules of heat we produce when we burn that fuel. So if we multiply this now, continuing on by the enthalpy of combustion, 715 kilojoules of energy are produced when we burn 1 mole of methanol. So now we know how much energy we get out when we burn that 1 liter of methanol. If we have that much energy, how long can we power a 60-watt light bulb? And so the next thing to do is realize that watts is joules per second, so we're going to convert this number into joules first. 1,000 joules per 1 kilojoule. And then finally, if we know the wattage, which is 60 joules per second, we can use that as a conversion factor to figure out how many seconds we can burn this light bulb for. So in 1 second, we use 60 joules. And finally, we get that. Now, the other annoying part about this problem is that the answer choices are in different units. So what we would find in terms of seconds is that this is 2.95 times 10 to the 5th seconds. The only answer choice that's in second is clearly not that number, so that's wrong. In terms of minutes, we divide that by 60 to get it into minutes. So that's going to be 4.9 times 10 to the 3rd minutes, which does not match that answer choice. And then finally, if we convert that to hours by dividing by 60 one more time, we get 81.9 hours, which matches choice D down here. All right, so if we burn 1 liter of methanol, which is about the size of this water bottle that's right in front of me, we would be able to power 1 light bulb for about 3 days, okay? So that sort of shows you that you need a lot of fuel to produce enough electricity, even just for a single home. And so this allows you to, again, just piece together a bunch of conversion factors. So there's not really any one specific chemistry concept here. It's just testing your understanding of these different properties and being able to use unit conversions to do that. So any questions on this one? This is a little, again, this question is a little bit out there, I admit, but there is a couple potential questions on the exam that you might get. You might not get this one, of course. There's always luck of the draw, that have sort of these types of concepts in it, using enthalpy of combustion and then using that to relate to some other quantity, like the amount of time when you have a wattage, all these things. So there's questions that are kind of similar to this. I just want to make sure we were aware of some of those concepts in case you get that one. So questions on this? All right, let's go on to number 10 then. So now we're on to the ideal gas section of the course, which we had the question earlier about the different gas laws, and we'll use one of them here. So we have a balloon that's filled with an ideal gas. It has a volume of 253 milliliters at 24 Celsius. What would be the volume if we increase the temperature to 86 Celsius? Now, if you think about this, hopefully you can. It's always helpful to think about things conceptually first before you start the problem. If we take a balloon and we start heating it up, provided we don't heat it enough to break the rubber on the balloon, would we expect the balloon to get bigger or smaller when we heat it up? Bigger, right? So we should hope then that we get a volume that's bigger than 253 milliliters. So the answer choices that are smaller than that, we could probably already eliminate. And then so let's see how we get that then numerically. So as I said, there's different gas laws that we wouldn't at least know what they are, but we can always start with PV equals nRT. And in this problem, it's just the volume and the temperature that are changing. We're not told how much pressure we have, so we're not going to worry about that. And the number of moles of gas in any closed container like a balloon would be constant as well. So the only things we have to worry about are volume and temperature. So we rearrange this, put those two variables on one side, V divided by T, which is equal to NR over P, and that ratio would then be constant. Okay? And so then we can write then that V1 over T1, the initial volume and temperature, that ratio will be equal to the ratio V2 over T2. And this is a statement of what's called Charles's law. So this is one of those three ideal gas laws that we want to be familiar with individually. The relationship between volume and temperature is called Charles's law. All right, so that's the equation we're using. What we're solving for here is the final volume, V2, which is given by V1 times T2 over T1. So the ratio of the two temperatures multiplied by the initial volume. So in these problems, if we take R out of the equation here, so and the units of pressure and volume, we don't really care what they are, but the temperature still needs to be in Kelvin. So our initial temperature T1 is 24 Celsius. So to get that into Kelvin, we have to add 273. So that's 297. And then T2 is 86 degrees Celsius, which we add 273 to get the final temperature in Kelvin, 359. Okay? So no matter what type of problem you're doing with ideal gases, the temperature has to be in Kelvin. And that's because the ratio of two Celsius temperatures will not be the same as the ratio of the two corresponding Kelvin temperatures because the scales are shifted. All right? In other words, they don't have the same 0 point, so you can't compare their ratios. So when we put the numbers in here, our initial volume was 253 milliliters. Our final temperature T2 is 359 Kelvin. Our initial temperature was 297. So the temperature units divide out. That'll give us an answer in milliliters, which is 306. So the volume increases from 253 to 306, and that corresponds then to answer choice C in this problem. All right, questions on how we use the ideal gas equation to relate things like volume and temperature to each other, or anything related to this? All right, we're halfway home, so let's keep going. All right, number 11, we have, in this case, a steel tank, which, if it wasn't obvious, tells us that the volume is fixed. We're not changing the volume here. And it's filled with 126 grams of nitrogen at 298 Kelvin, which gives a pressure reading of 235 kPa. What will the new pressure be if 96 grams is added and the temperature cools to 273 Kelvin? There's actually a few different ways we can approach this problem, so one is we don't know what the exact volume is, but we have enough information to find it if we wanted to. So we know how much nitrogen we initially have, we know the initial temperature, we know the initial pressure. So if we wanted to, we could actually solve for what the volume of the container is and then use PV equals nRT again to figure out what the new pressure would be. That's one way to do it. The other way to do it is to just, again, use ideal gas equation to derive a new equation in terms of which parameters are actually changing versus which ones are staying the same. So PV equals nRT is our starting point. In this case, we know that the volume is fixed. We're told that it's a steel container with a fixed volume, but we know that the pressure, the number of moles, and the temperature are all changing. So we can isolate those three variables and say that pressure divided by number of moles times temperature is equal to R over V, and this ratio would then be our constant. So we can write this then as P1 over N1 T1 equals P2 over N2 T2. And this equation doesn't have like a specific name associated with it. This isn't one of our named gas laws, but we can get it from the ideal gas equation and use it. And in this case, we don't need to know what the volume is. We could have solved for the volume, as I said, that's another way of doing this, but in this case, if we just leave it out because it's constant, we can derive a new equation. And then what we're looking for is the final pressure, P2, which is the initial pressure times the ratio N2 over N1 times the ratio T2 over T1. Okay? So we need all of these things to put in there. Number of moles that we have at the start and the end, number of the temperature at the start and the end, we start putting things in. Alright, so our initial pressure is 235 kPa. We don't have to change the units as long as we're not using the value of R in our calculation. So that's the other advantage of sometimes rearranging the ideal gas equation. You can be a little bit more flexible with the units for pressure and volume especially. Now what we need to do is find the number of moles for each of these. Okay, so N1 is the initial number, the initial amount of nitrogen we had, which is 126 grams. We convert that into moles. We have to recognize that it's N2, so the molar mass is 2 times 14 or 28. So initially we had 4.50 moles of nitrogen. But we have to be careful with the wording of the problem here. So we're adding 96 grams to that. So the final number of moles that we have is going to be the sum of the two. It's going to be the amount we started with plus the amount we added. It's not just the amount we added, it's the total number we have after the addition. So we're adding 96 grams to get N2, which means that the final number of moles that we have is the amount that we initially started with, plus the 96 grams also converted into moles. So we add an additional 3.43, I think it is, and that comes out to then a total of 7.93 moles. So it has to be the total amount of gas we have, not just the amount we added to it. It's the sum of the two. So 126 plus 96 at the end, convert that into moles, which comes out to this number. So that's our value for N2, which is 7.93 moles. The final temperature, T2, was 273 Kelvin. And then in the bottom we have initial number of moles, which is 4.50, and the initial temperature, which was 298. So we're changing all these things, we're finding out what the new pressure is, and it comes out to 379.4 kilopascals. Because again, that unit carries through to the end, doesn't cancel out with anything. And so that's the number that we would add in the blackboard, 379.4. So the biggest caveat here was to make sure we knew that whenever we're using PV equals nRT, it's always in terms of the total number of moles of gas present, not in terms of how much we've added or subtracted, if that's the situation that we're dealing with. Questions on this one? Yeah, because I can't write, or because it doesn't look like that. It actually is that. It shouldn't be. So it's 4.5 mole. Thank you. Any other questions or things that I screwed up? All right, let's go on then to number 12, if there's nothing else. All right, this one we're talking about gas stoichiometry. So we have a reaction between two gases, NO and Cl2, and we're forming NOCl. If we're using 32.5 liters of NO and 21.2 liters of Cl2 at STP, how many liters of NOCl form? So the first thing in any stoichiometry problems, let's write a balanced chemical equation. And what it looks like we're going to have to do is, if we have two chlorines on the reactant side, we have to put a coefficient of 2 there, which means then we also need 2 NOs. So it's 2 NO plus 1 Cl2 to give 2 NoCl. That's the simplest way to balance this. And then what we have to do is we're told amounts of each reactant. We have 32.5 liters of NO, 21.2 liters of Cl2. And thinking back to things we learned earlier in the course, anytime we know the amount of 2 or more reactants, we have to figure out which one the limiting reactant is before we can figure out how much product forms. So we have to determine the limiting reactant. Now, back when we first learned how to do stoichiometry, we learned that to determine the limiting reactant, you find what's called a stoichiometric ratio for each reactant. So we have NO. And the way we conventionally defined it was the stoichiometric ratio was the number of moles of that reactant divided by the coefficient, which we could do here. There's nothing wrong with doing it that way here. We can use the volume. We can use the fact that we're at STP, which tells us that the temperature is 273 Kelvin, the pressure is 1 atmosphere. We can convert that into number of moles. However, that's a step that's not necessarily required in an ideal gas problem, because from PV equals nRT, volume and number of moles are proportional to each other. That's what we refer to as Avogadro's law, which means that in a gas stoichiometry problem, you don't necessarily have to convert it into moles if you know how much volume of reactant you have and all of them are at the same temperature and pressure as they are here. So because of this, we can actually just use the volumes directly, because the ratio of the moles that react with each other is going to be the same as the ratio of volumes that react with each other. So what we can do then is to find stoichiometric ratio for NO. We can just take its volume, which is 32.5, and divide it by the coefficient, which is 2. And we can do the same thing for Cl2. We take the volume of Cl2 that we have and divide it by its coefficient, which is a 1. So that comes out to 21.2. So this is the smaller stoichiometric ratio in terms of volume, which makes it the limiting reactant. And even if we had converted it into moles, which would have been fine, we would have still gotten the same conclusion that NO is a limiting reactant. And the reason that it's nice to do it this way is also because the final answer we're looking for is the liters of product. So if we had converted into moles of each reactant and moles of product, we have to do more steps to convert back into liters. It's just a lot of additional work. So we can work in volumes directly when we're talking about reactions of gases. And so what that means then is the volume of NoCl that forms in liters. We start with our limiting reactant, so we had 32.5 liters of our limiting reactant NO. And because liters and moles are proportional for ideal gases, we know that the mole ratios tell us the ratio of the volumes as well. So we have a coefficient of 2 in front of NoCl, which means that 2 liters of NoCl form for every 2 liters of NO that react. So it's a 2-to-2 ratio, which is just simplifies to 1-to-1, meaning that if we react 32.5 liters of NO, we will also form 32.5 liters of the product, NoCl, provided they're at the same temperature and pressure, which they are. Okay? So 32.5 will be the number that we would put in, but we don't have to go through the extra steps of converting into moles, because at the end we'd have to convert back out of moles anyway. We'd just be undoing what we already did. And for ideal gases, the ratios of volumes that react is equal to the ratios of moles that react, so there's no really necessary reason to do that. So questions on this one? So I do encourage you to use this a little bit of a shortcut if it's appropriate to do so, because it allows you to save some time when you're talking about reactions of gases, not always having to convert into moles if it's not required. All right, anything else on gas stoichiometry? Yeah. Yeah, so because these are at STP, so reminding us what I just covered in class the other day, STP is standard temperature and pressure, which means 1 atmosphere, 273 Kelvin. So at these exact conditions, 1 mole has a volume of 22.4 liters. So we could have, if we needed to do moles, or if we were more comfortable doing that, we could have just taken these numbers, divided by 22.4, using that as a conversion factor to get into a number of moles without having to do the full PV equals nRT, which is where that number comes from anyway. But yeah, it only works for STP, so be a little bit careful about that. The fact, the shortcut that we took using volumes instead of number of moles, it works for any condition. It doesn't have to be STP, as long as the gases that you're reacting with each other are at the same condition, same volume, same temperature. same pressure, not necessarily same volume, but same pressure and same temperature. So in this case, it didn't matter that it was STP as long as the two were the same as each other. You could use that shortcut. You just couldn't use the 22.4 liter shortcut unless it's STP. Questions? Other ones? All right, going on then. In this question, we have a 250 milliliter gas bulb filled with 379 grams of a gas, and it's at STP also. Which of these is likely to be the gas? All right, so again, we're working at STP, so we know that our pressure and temperature are 1 atmosphere, 273 Kelvin. And just like we did in some other problems earlier in the course, typically speaking, if you want to identify an unknown sample of a substance, the way we do that is we find what its molar mass is. So we saw some ways we did that earlier with titrations. I think some of the mass percent problems we did earlier in the course, you could find the atomic mass of the element and identify it. So typically speaking, if we're trying to find something that's an unknown species, we try to find out what its molar mass is. So what we should think about then is, how can we use the ideal gas equation to do this? And we have this equation that, PV equals nRT is our starting point, and we can rewrite number of moles in terms of mass, where that number of moles is given by the mass of the gas divided by its molar mass, which means then we can rewrite the ideal gas equation as PV is equal to mass divided by molar mass times RT. I think somebody's at my front door. Oh no. Anyway, so PV equals mass divided by molar mass times RT. And so then what we're solving for here is the molar mass of our unknown gas. So we can just write this equation as molar mass is equal to mass times RT over PV. This is very similar to the density equation. We could have also just calculated the density using the mass and the volume and put that into the standard form of the density equation, but we could also just start with this form of the equation, rearrange it whatever you're more comfortable with. So we rewrite the ideal gas equation in terms of mass and molar mass, and then we solve for what the molar mass would be, and that's what we get. So we just have to plug the numbers in. 0.379 grams is the mass. R is 0.0821 liter atmospheres per k mole. The temperature at STP is 273 Kelvin. And then the pressure at STP is 1 atmosphere. And we're told that the volume is 250 milliliters. That needs to be in liters for the ideal gas equation. So we have to divide that by 1,000, right, as 0.25 liters. And so what we get in this case is 33.98 grams per mole, keeping probably more significant figures than we need. And so what we have to do is figure out, okay, this is our unknown molar mass. Which of these gases has a molar mass that's closest to 33.98 grams per mole? So phosphorus trihydride, or phosphine as we call it, pH3, the molar mass for this is 1 phosphorus, which is 31, plus 3 hydrogens. That one is 34, so that's a pretty good match. Make sure it's the closest one. SO2 is sulfur, which is 32, 2 oxygens, which is another 32, so that's 64. N2 is 2 times 14, which is 28. So you have to get these from the periodic table. I think we all know how to do molar masses now. And then argon is just an element, so its molar mass is just the atomic mass directly from the periodic table, which is about 40. So the one that's certainly closest to these is A, which is pH3, which has a molar mass of 34. So we find what the molar mass is, we match it up to which one is closest to, and that's going to be the one that we identify as our unknown gas. Okay, questions? Yep. Well, we didn't cross them out. They're still here, right? How come we're not able to? Well, because they're constant, but we're not talking about like a gas changing anything, right? It's not going from one set of conditions to another. It's just at this temperature, at this pressure. So we're going to use we could ignore the pressure because it's 1, but the temperature is 273, and if you're using the ideal gas equation, that temperature still has to go in as whatever number it is. So if it was a situation where we have SDP and then the volume and number of moles are changing or something, you could have then dropped those out. But in this case, it's just one gas, one set of conditions, so we're using the ideal gas equation. We need to keep the temperature in there and the pressure ideally as well. Yep. Yes, that's exactly identical way to do it, or not identical, but equivalent way of doing it. So the suggestion in the back, which works just as well, is we can, since we know the volume and we know the temperature and the pressure, we can use PV equals nRT to figure out how many moles of gas are in there, and then we can take the mass that we're given and divide it by number of moles to get molar mass, and you'll get the same number, and it works exactly the same. So that's a equally valid way of doing this problem as well. All right, anything else? All right, on to number 14. So more ideal gas problems. We have a tank that contains 3.25 atmospheres of N2 with a volume of 9.3 liters. We connect it to a tank that has 5.33 atmospheres of O2 with a final volume of 15.2. If we open the valve between the two, what is the final pressure after the gases have mixed? So we're taking that no chemical reactions occurring, the temperature is staying the same, but the pressure as the two gases mix together is going to be potentially something different than what we started with. So this ends up being what's, in the context of Dalton's law of partial pressures. We're mixing two gases together, which means that the total pressure in the mixture is going to be the partial pressures of each. Now we can't just take the two numbers that were given, 3.25 and 5.33, and add them, because when we mix the gases together, their volumes are also changing as well. Because once we open the valve and allow the gases to mix, both gases are going to fill the entire volume that's present, and so you can't just assume that the pressure of each individual gas is going to stay the same because it's occupying a different volume. So this partial pressure that we're going to add together is the partial pressure that you get after mixing them together, which is important. So we have to find out what those numbers are. And the way we're going to do this is we're going to treat each individual gas separately. We want to find each partial pressure, so we treat the gases separately. The pressure and the volume are changing, but we're telling you that the number of moles of that gas is not changing. We're not letting any gas leak out. It's still the same amount of nitrogen that we started with, same amount of oxygen that we started with. Temperature we're saying is constant. So this pressure times volume is equal to constant. So what we're going to do is, for each individual gas, we're going to set up Boyle's law. The P1V1 equals P2V2. And then for each gas, we're going to solve for what the final pressure is after we allow the two gases to mix together when the volume is changing. So the final pressure for each gas is going to be its initial pressure times its initial volume divided by the final volume that the two gases occupy. We're going to do that for both gases. That's going to give us their partial pressures. Then we add them together at the end. So for N2, its final pressure we had initially 3.25 atmospheres in a volume of 9.3 liters. And then when we mix them together, we have to keep in mind what is this final volume V2. So V2 is going to be the sum of the two volumes. Initially, this one occupies 9.3 liters. The other tank that had oxygen in it was 15.2. So the sum of those two volumes is going to give us what the final volume is when they mix together, 24.5. Okay? So once you mix the two gases together, they occupy the full volume, the combined volume of the two tanks that we allowed to mix. And so that's going to be our V2 for both of them is 24.5 liters. So the partial pressure of nitrogen after mixing together is 1.23 atmospheres. And then the partial pressure of O2 after mixing is going to be its initial pressure and volume, which was 5.33. Its initial volume was 15.2. And it's still occupying the same final volume of 24.5. So the partial pressure for O2 after mixing is 3.31 atmospheres. So both partial pressures drop because they're now occupying a larger volume. And then when we add the two together, we get 1.23 atmospheres for nitrogen, 3.31 atmospheres for oxygen, and the sum of those two is the total pressure, which is 4.54. choice D in this case. All right, so this was an application of two things. It was an application of Boyle's law to figure out what is the partial pressure of each gas after they're allowed to mix together and they occupy the larger volume. And then once you have the partial pressure of each gas, Dalton's law tells us that we can add those two together to get what the total pressure would be. Any questions on this one? Okay, I don't think I did a homework or a question like this in class. You may have seen it on the homework, and this is how we would approach something like this when we're mixing two gases together. Is there a question in the back? Sorry.
How did you use the 16.2 again for that one? For O2?
So that's the initial volume of the O2 tank. So we're told initially that the tank containing O2 has a pressure of 5.33 atmospheres with a volume of 15.2 liters. So that's the initial volume that we had for oxygen. The final volume for both of the gases once they mix is the combined volume of the two tanks after you allow them after you open up the valve between them and allow them to mix with each other. Another question? I mean, probably in this situation, no. I suppose if we're telling you what the final pressure is, you could maybe find out what the temperature is, right? Because, in this case, the final pressure is not known, but if we said, well, the final pressure is this, what would be the temperature? You'd have to then go back to PV equals nRT to solve for the new temperature once you know what the final pressure is and you have the final volume and total number of moles. So there's some slight variations, but in this case, with the information we gave you, that's the only thing you could find. And we're telling you that temperature is constant. You have everything else you need in this situation. But yeah, there's possible other ways we could do it, but not many. Yep.
So, just a refresher, Dalton's law you said is something like
Combined pressures. So Dalton's law tells us that if you have a mixture of gases, the total pressure is equal to the sum of the partial pressures of the individual gases, however many you have in your mixture. And the other way of writing Dalton's law, which is very useful for some types of problems, we didn't need it here, is that the partial pressure of a gas in a mixture is equal to the mole fraction of that gas times the total pressure. So you'll also use this form of Dalton's law as well if you're trying to find especially what the partial pressure of one of the gases is if you know the total pressure in the composition of the mixture. So mole fraction being the fraction of the number of moles of that gas divided by the total number of moles. So if you know the composition of the mixture, you can use this equation to find out the partial pressure of one of the gases. So these are the two different ways of thinking about Dalton's law, or the two sort of equations that come out of it that you might use in different situations. Anything else? All right, on to number 15. So 15, we're talking about diffusion of gases. So we say that a 2-atmosphere sample of effusion effuses through a small opening in a time of 2 minutes. If a sample of an unknown gas under the same conditions takes 3.9 minutes to diffuse, or I guess I should say effuse, what is the molar mass? That word doesn't change anything how we do this problem. It's just not precisely worded. So this is Graham's law, and we're talking about the diffusion or effusion of two gases and either the rate at which they occur or the amount of time that it takes. So the standard form of this equation is in terms of rates of effusion or diffusion. So for these two gases, the rate of N2 divided by the rate of the unknown gas X is equal to the ratios of molar masses but inverse. That's sort of the standard form of the equation that we introduced initially. But in this case, we're talking about the amount of time that it takes. And so what we should recognize is the gas that has the faster rate is going to have the smaller time. The gas that has the smaller rate is going to take a longer time. So if we're going to use times instead of rates, we have to invert one side of the equation. So if we're talking about the ratio of the two times, the time that it takes N2 to diffuse or effuse, divided by the time it takes for the unknown gas, that's going to be directly related to the molar mass ratios. As a square root, of course. So this is the form of the equation we want to use because we're given the amount of time that it takes. And we should, again, think about things a little bit logically or conceptually before we start just chugging away with numbers. And we should recognize that if a gas is moving slower, it takes longer. The heavier gas should be the one that's moving slower. So we see that N2 takes 2 minutes, our unknown gas takes 3.9 minutes. So that would tell us then that the unknown gas must be heavier than N2 because it takes a longer time to fuse, which means it's moving slower. So we should get a number that's bigger than the molar mass of N2. And again, so it's helpful to check answers that are reasonable. So if we put the numbers into the equation, what we see is that it took 2.0 minutes for N2 to fuse, 3.9 for our unknown, and that's equal to the square root ratio of the molar masses. So the molar mass of N2 is 2 times 14, or 28. So that means the number we get should be bigger than 28 because our unknown gas is moving slower. And that's going to be our unknown, or in this algebra expression, is the molar mass of X. So we have to do a little bit of algebra. We have to cross multiply. We have to square both sides and all that stuff. So if you have trouble with the algebra, definitely refresh it or come see me afterwards for a quick refresher. But I think most of us are good enough at algebra to get this. And what we solve for then is a molar mass of 106, which is choice B. All right, so we can, again, knowing that nitrogen has a molar mass of 28 and that our unknown gas should be larger than nitrogen or heavier than nitrogen, we could have eliminated those two without even doing the math. And then it just comes down to a coin flip. But if you, of course, set up the problem, it becomes better than a coin flip by getting the right answer of 106. Questions on this one, or the concept of Graham's law? Yep. So the ones that are, the ones that are directly proportional will just be the amount of time that it takes. So the one that has a longer time has a higher molar mass. Both the rate that it's effusing at, or the amount of gas that effuses in a certain period of time, both of those would be inversely related to the molar mass. So time's the only one where you have to flip one side of the equation. If we're talking about the ratio of the rates or the ratio of the amounts of gases that effuse or diffuse, you'd use this form of the equation up here. We have to flip one side of the equation if we're talking about time instead. Anything else? Okay. 5 more, and these are mostly, I think, conceptual, so it should go a little faster. Here we're looking for which statements about ideal gases are false. So we have 4 choices, and then one that says 2 of them are false. So the first one, in a mixture of 2 gases A and B, the total pressure depends only on the total moles of A and B, not their identity. And this is kind of a statement of what the ideal gas law tells us, or more specifically Dalton's law, which is that if you want to know the total pressure of a mixture, it just depends on the total number of moles. It doesn't matter what those gases are. So none of the ideal gas equations, both PV equals nRT in this case, or Dalton's law, which is in terms of partial pressures, neither of those care what the gas is. So if the mixture is A and B and the total pressure depends only on total moles, that one's going to be true. All right, so anytime we're trying to find the total pressure of a mixture of gases, it only depends on how many moles we have, not what they are. Choice B, samples of helium and O2 at STP have the same average kinetic energy. So if they're both at STP, that means they both have the same temperature, 273 Kelvin. And remember that kinetic energy is directly proportional to temperature. And so if we have the same temperature, they're going to have the same average kinetic energy. So that one would also be true. Choice C we're talking about, and so kinetic energy only depends on temperature. That's the only factor that matters for kinetic energy. However, if we talk about kinetic energy at a given temperature, so choice C says if we have those samples of helium and oxygen, they have different average molecular speeds, and then we say that O2 is higher. So at a given temperature, they have the same kinetic energy. But remember that kinetic energy is defined as 1/2 times mv squared. So the velocity that we have is going to then depend on what the mass of the gas is, or and specifically the molar mass. So if the 2 gases are at the same temperature with the same kinetic energy, the one that has the larger mass is going to have the smaller velocity. The one that has the smaller mass is going to have the larger velocity. So in this case it says they have different molecular speeds. That's true because O2 and helium have different masses. However, O2 should be the one that's the smaller velocity because it's the heavier gas. Okay? So this one is false because helium should be moving faster than O2 when they're at the same temperature, because helium is a lighter gas, so in order to have the same kinetic energy, it needs to have a larger velocity. And then finally, choice D, deviations from ideal gas law are smallest at high pressure and low temperature. This one is exactly the opposite of what's true. So the ideal gas law, you have the smallest deviations when the gas molecules are spread as far apart from each other as possible and when they're moving as fast as possible. So to have minimum deviations from ideal gas behavior, you want to have low pressures, which puts the gas molecules really far apart from each other so they don't interact. And you want to have high temperatures such that they're moving around really fast and they don't interact with each other for a very long period of time. So this one is also incorrect because the deviation should be smallest when the pressure is low and when the temperature is high, so it's the opposite. So that means choice E is the correct answer. Both of those, C and D, would be false. All right, questions on the concepts related to kinetic molecular theory, ideal gas law, or real gases, which is what this problem dealt with. Yep. D is wrong because the deviations would be smallest when the pressure is lowest and the temperature is highest. And that's because for... so remember that what the ideal gas law assumes is that the key assumption is that there's two key assumptions that it assumes. One is that the gas molecules have no volume themselves, that basically all the volume is empty space. And then the other assumption of the ideal gas equation is that the gas atoms or molecules don't interact with each other at all. They don't even know that each other's there. And so both of those can be wrong, and they can cause deviations from the ideal gas equation. And those deviations are going to be the largest when the gas molecules are closest together. Because when the gas molecules are really close together, they interact a lot. So that means you're going to get deviations from ideal behavior. If you want the smallest deviations, though, what you want is the gases to interact the least, which means they should be spread really far apart, having a low pressure or a large volume, or they need to be at a high temperature so that they're moving really fast and that they don't interact with each other. So anytime you're asking about deviations from ideal gas behavior, they're going to be smallest under conditions of low pressure and high temperature. So it's helpful to remember that and try to at least understand a little bit about why that's true. Anything else? All right, on to 17. So here we're finally into the chapter 9 material, just a few questions on this. So which intermolecular forces are present in a sample of SF4? So we're giving you a choice here. We have London dispersion forces, covalent bonds, dipole-dipole forces, two of these or all of these. So the first thing we have to realize is if we look at the answer choices, London dispersion forces, everything has London dispersion force. It doesn't matter what it is as long as it has one or more electrons, because London dispersion forces are the interactions that are caused by what are called instantaneous dipoles, which are these sort of imbalance in electron distribution that occurs on small time scales in a molecule. So the point is, everything has London dispersion forces. So we don't even have to think about that one anymore. We'll give this a second to catch up and hopefully not crash. All right. So everything is going to experience London dispersion forces. So it doesn't matter what it is. So that one we know is going to be an intermolecular force that's present in a sample of SF4. The next one, covalent bonds, are we going to ever pick this answer choice? And why not? Yes, I think I heard the answer out there somewhere. So the reason that this is not, that we wouldn't pick this is because this is not an intermolecular force. Remember, this is the distinction between intermolecular and intramolecular forces. Intermolecular forces, what we're asked about here, are forces of attraction between separate molecules. Covalent bonds are the forces that hold together a single molecule. So covalent bonds or any type of bond is not considered an IMF. It's a totally separate concept, and so we would never want to pick that as an answer choice. So this choice was mainly just to make sure we understand the difference between those two things. And then the last one is, does this have dipole-dipole forces? To evaluate this, we need to know whether the molecule is polar or nonpolar. So we can't just look at the formula and be able to tell. We have to draw it out. So as a review of Chapter 4, if we have SF4, we have sulfur and fluorine. So we have 6 valence electrons from sulfur. We have 4 fluorines that each contribute 7. So that would come from the periodic table by looking at the group numbers. And so this has 34 total valence electrons. So if we want to figure out if this is polar, we have to draw the Lewis structure. We have to think about whether that Lewis structure then results in a polar or nonpolar arrangement. And then that's going to tell us whether or not this has dipole-dipole forces. So when we draw the Lewis structure of SF4, after completing the octets of all the fluorines, That uses up 32 of our electrons. We've done 4 octets. So that means there's 2 more left that have to go in the central atom. So this gives us an AX4E structure. And as we learned about when we were talking about molecular polarity, we could draw the geometry out. This would be a seesaw molecule. But anything that has just one lone pair is going to be polar. So it doesn't matter whether it's AX2E, AX3E, AX4E, AX5E. Any of the ones that have one lone pair are polar. So because this is a polar molecule, it will have dipole-dipole forces. Any polar molecule experiences dipole-dipole forces. So we're going to choose that as also a correct answer, meaning that choice D, 2 of these would be the one that we would pick as being the types of intermolecular forces. The only intermolecular force that SF4 does not have is hydrogen bonding. It doesn't have any bonds, well, it doesn't have any hydrogens at all, but it certainly doesn't have any hydrogens bonded to either fluorine, oxygen, or nitrogen. So hydrogen bonding would be out if that was a choice, but the other 2 intermolecular forces, London dispersion forces, is present in everything. Dipole-dipole forces will be present in anything that's considered polar. Okay, questions on this one or on the concept of intermolecular forces? So this is one of the more recent things we've done, so if you want to spend a little more time on it, that's fine. If not, we will move on to the next one, which I think also deals with the same concept of intermolecular forces. So here we're talking about properties that depend on intermolecular forces. The reason that they're important is because they dictate some of the key properties of molecules when they're in condensed phases especially. And we want to know which of the following does not increase with the strength of the intermolecular forces. Melting point, boiling point, viscosity, surface tension, or ideal gas behavior. So melting point and boiling point are those 2 phase change temperatures that we've talked about, and we'll get a little bit more detail about them even a little bit later. And so those are the temperatures at which, the melting point being the temperature at which a substance goes from solid to liquid, the boiling point the temperature at which it goes from liquid to gas. And we should recognize that both of those depend strongly on the intermolecular forces, because if the molecules are held together by stronger forces, you have to go to higher temperatures to break up those molecules into either the liquid phase or the gas phase. So both melting point and boiling point increase as the strength of the intermolecular forces increases. So both of those are going to be true. Those would both increase if you have stronger intermolecular forces, because it means you have to go to higher temperatures to break those forces and get the molecules from either solid to liquid or liquid to gas. The next one is viscosity. The next 2 are the properties of liquids that we learned about. So viscosity is basically the resistance to flow, or how thick the liquid is. And this one would also increase with intermolecular forces, because if the molecules are held together more tightly, they don't flow as fast. They're sort of sticking to each other, and so you would get a higher viscosity if you have stronger intermolecular forces. And then surface tension is the resistance of a liquid to change its surface area, or in other words, if you go to the surface of the liquid, how difficult is it to penetrate that surface? And that would also increase as the intermolecular forces increase, because surface tension is caused by molecules that are under the surface sort of pulling on the molecules at the surface and kind of holding them into a tight arrangement at the surface because of those strong forces. And if those forces are stronger, the surface tension would also be stronger. So the point being, all 4 of these key properties, melting point, boiling point, viscosity, surface tension, they will all increase as the strength of the intermolecular forces increases. Now the last one, ideal gas behavior, is the gas going to be more ideal or less ideal if the intermolecular forces are stronger? It would be less ideal. This is the only one that's left. It has to be the right answer. And so it doesn't increase because, as we just talked about in addressing a question that we had on a recent previous problem, when you have ideal gases, you're assuming that there's no interactions between them. But if there are, in fact, strong intermolecular forces, that's going to cause the gas to behave less ideally. So the strength of the intermolecular forces will cause worse ideal gas behavior, more deviations from the ideal gas law. So this one is going to be false, which makes it the right answer, because we're looking for the one that does not increase with intermolecular forces. All right, so the 2 types of things we'd ask you about then with intermolecular forces are sort of reflected in these last 2 questions. Identifying the types of intermolecular forces and which ones are stronger and weaker than others, and then using that knowledge to predict something about certain properties, at least the relative relative changes in a property between 2 substances as a function of intermolecular forces. So questions on those topics? Yeah, you have one?
Can you explain how you explain surface tension again?
All right, so surface tension is, so you can think about what it means in sort of a visual sense, which is, You know how certain insects can float on top of water, and that's because there's a tension at the surface, which is a resistance to penetrating that surface or a resistance to spreading out that liquid more than it already is spread out. And what causes it is that you have the molecules at the surface are not surrounded by other molecules on all four sides. They just have molecules below them, right? So those molecules at the surface are getting pulled down by the molecules that are below them by those intermolecular forces. And it's that downward pull of the molecules below them that's causing them to resist any motion at the surface, to be more tense at the surface, to have less ability to flow or spread out at the surface. So it's caused by the intermolecular forces between molecules at the surface with those that are below it, and that sort of keeps the surface more rigid than the ones, because they don't have molecules surrounding them in all directions, so there's a net downward pull of the molecules at the surface.
And then it would be easy because
We're looking for the ones that does not increase as the intermolecular forces increase. So liquids that have stronger intermolecular forces tend to have higher surface tension. So if you compare like water to any hydrocarbon, let's say pentane, C5H12. C5H12 is nonpolar, so it has weaker intermolecular forces than water, so it has smaller surface tension. And again, the idea of surface tension is that at the surface of the liquid, let's say with water, I don't know if I'm going to be able to draw this very well or not, you have all these molecules sort of aligned on the surface. And they're sort of being pulled on by molecules below the surface via these hydrogen bonds. And so on. So you have these molecules at the surface that are sort of being pulled down by the ones below it. The molecules that are in the bulk, that are below the surface, they're surrounded on all sides by molecules. So they have sort of equal intermolecular forces in all directions. The ones on the surface don't have any molecules above them, so in that there's a downward pull of those ones, and that's what gives rise to this surface tension, sort of keeping them in place at the surface. There's not as much free motion at the surface. That's what gives you that surface tension. All right, any other questions on these properties? All right, the next one deals with cubic unit cells. So to be clear on what's on the test and what's not, we'll talk about the cubics in I guess to some extent hexagonal structures. So the face-centered cubic, body-centered cubic, simple cubic structures. We won't have anything about ionic compounds on the midterm. That'll only be on the final, but those two topics are closely related anyway. So here we just talking about a partially filled cubic unit cell, and it has 4 corner atoms, it has 2 face atoms, and it has 4 edges. We want to know how many total atoms are there in the partially filled cell. So what we do is we think about where these different atoms are located in the cube. All right, so if we have a cubic unit cell, what we're saying here is that we're going to put one atom on the face. So let's look at the front face here. We put one right in the middle of that front square. We have one atom. We have atoms on the corners, and we have atoms on the edges as well. So those are the 3 positions we're talking about here: faces, corners, and edges. And we want to know how many different atoms do we have when we have 4 on the corners, 2 on the faces, and 4 on the edges. So we have to just learn how to count the number of atoms. We have to recognize that if we have 4 corners filled, each corner is shared by 8 adjacent unit cells. So think about taking these cubes like little blocks and stacking them in all different directions. Each corner is going to be a boundary between 8 different ones, 4 that are below, 4 that are above that corner. And so what we have then is each corner counts as 1/8 when we're counting atoms in a cubic unit cell. We have 2 faces that are filled in this case. Each face is going to be the borderline between 2 of those unit cells as we stack them together. So each face counts as a half. And then the last one is we have 4 edges. And the edges are shared between 4 cells. 2 one that's in front in this direction, 1 that's on the side, and then 2 more coming out. So we have a total of 4 that are shared by edges. And think of it as stacking cubic blocks if you enjoy that activity as a child, or maybe still do. And you can think about edges sharing between 4 cubes, so you count those as a fourth. So whenever we count corners, they count as an eighth each. Faces are a half, edges are a fourth. In this case, we're partially filling the unit cell, so we could have up to 8 corners, but we're telling you that there's only 4 in the corners. We could have up to 6 faces, but only 2 of them are filled here. We could have up to 12 edges, but only 4 of them. And so in this combination, what we get when we add these numbers together is 2.5. Obviously not a very physically relevant situation because you can't have half of an atom, as you can't split the atom in half. But this is what we would get when we count those using the numbers that were given and the rules that we have for counting positions in a cubic cell. So questions on this one? Yep. That wouldn't give you the right answer, right? Just add it. So you have to count for how many of each atom we have in those positions as well. So it's 1/8 times however many corners we have, which in this case is 4, because this is partially filled. So that's you do remember these 3 numbers though: 1/8 for a corner, half for a face, 1/4 for the edges, and then the last type, which isn't in this problem, is if you have an atom that's completely inside of the unit cell, either in the body-centered position or any of the positions that are inside of the cell, that counts as a full atom. It's not shared at all. But anytime they're shared along the edges, the sides, or the corners, you have to then account for that, and then when you count them up, you multiply by that. Okay. Question? Yeah, another question here? Okay. Anything else? All right, last one. Here we go. So this one is dealing with properties of different types of elements. So an element is found to be a good conductor of electricity, has a high boiling point, and is malleable. Which of the following could be the element? So we have sulfur, phosphorus, neon, gold, and iodine. And so what we essentially want to do in these types of problems, we're talking about, bulk properties of an element, and we want to know what it is. We basically are identifying it as either a metal or a non-metal, because metals and non-metals have some very different properties from each other. So let's talk about what those are and then identify which one fits the situation that we have here. So if we're talking about their electrical conductivity, metals are all good conductors of electricity. And except for a few rare exceptions, non-metals tend to be insulators. Graphite being the exception. It's a non-metal that's a good conductor, but the vast majority of non-metals are insulating in their behavior. We have, in terms of their physical properties, their physical deformation, or their mechanical properties as they're called, metals are what are called malleable, which means that we can bend them and shape them in different ways without them breaking very easily. But most non-metals are brittle, meaning that even if they're a solid, if you try to shape that solid, it's just going to crumble. Okay, so that's the difference between them in terms of their mechanical properties. And then finally, in terms of their boiling points, metals have high boiling points. Because in a solid metal, you have this sea of electrons, as we call it, these loosely held valence electrons that are shared between all the atoms. And if you want to boil the metal, you have to break all of them apart. You have to break all of those attractions between the valence electrons and the nuclei. So that's hard to do. Whereas nonmetals, most nonmetal elements are nonpolar substances, like all these diatomics that we have, N2 and O2 and Cl2, which means that they have very low boiling points because they have very weak intermolecular forces. So the substance that we have here is a good conductor, has a high boiling point, and is malleable, so that identifies it as a metal. And so all we have to do is look at this list of elements to figure out which one's the metal. So we have sulfur, phosphorus, neon, gold, and iodine. So remember, we have this sort of staircase here that divides nonmetals from metals. So anything to the right is a nonmetal. So sulfur, phosphorus, neon, and iodine are all clearly nonmetals. So that's P, S, I, and E. Those for nonmetals. Gold is the last one. It's in the transition metal series, but all those are still classified as metals, of course. It's to the left of the staircase, so this is the metal that we have, those answer choices. So the correct answer for this would be D, which is gold, because it's the only one of these that's a metal, which means it's the only one that we would predict to have those properties. Yep?
Is lead anything
No, there is. So why didn't I put a lattice energy problem in here? That's a good question. No, there should be lattice energy on the test. Why did I not include it though? It might be mixed in with some other things, so it might not be that everybody gets a lattice energy question, but there are some. So yeah, so definitely review lattice energy. I didn't go through that here, but there should be some available in the homework questions in the book and stuff. So if you have questions on it, of course, we can deal with that individually. All right, so that takes us to the end if there's no more questions. And I will be in my office for most of next week. The hours that I'll be there are posted in Blackboard, so if you have any last minute things you want to talk about before your exam, please feel free to stop by during any of those times, and I'll see you then. All right, so I'll see you guys next week then. I'll get this video posted tonight.